We will continue the discussion on the heat equation in more than one variable, and in the last class we started discussing an example which is a mixed initial boundary value problem uh, involving an infinite circular cylinder, and this was the physical situation. From the initial conditions at t equal to 0 and the boundary condition, uh, and the geometry of the problem, we see that there is no variation in the z direction. So the problem essentially reduces to a two-dimensional heat equation. Okay, so that's what we deduced from the initial boundary conditions and the geometry of the problem. Okay, and again looking at the geometry, so this is just a circular domain, and A is the radius of the circle in the xy plane, centered at the origin. We can look for again radial solutions. Okay, so uxyt is equal to u of rt. Okay, so x is equal to r cos theta, y is equal to r sin theta, and r square equal to x square plus y square. So these are the polar coordinates in two dimensions. One word of caution here: this change of variables from rectangular coordinates to polar coordinates, it is singular at r equal to 0, so we should avoid that r equal to 0. So while seeking a solution in the radial form, we also require that this whatever solution we get should remain bounded as r tends to 0 and for all t, because in the original problem there is no problem at r equal to 0. Okay, so with this change of variable, there may appear a singularity at r equal to 0, but then we should look for solutions which remain bounded as r tends to 0. Okay, so again just writing the Laplacian in two dimensions, so let me just write. So in n equal to 2, okay, so we have this del square by del x square plus the Laplace operator in rectangular coordinates converted to this. One by r del by del. Okay, you see that's division by r, so this always should remain greater than 0. So in general there will also be a theta part. Okay, so something theta variable, but in this case it is not there because we are assuming u is only a function of r. Okay, so then the problem reduces to, so this heat equation becomes in rt coordinates ut is equal to del square u by del r square plus 1 by r del u by del r, and the initial condition becomes ur0 equal to u1 for 0 less than r less than a. So again I am avoiding that r equal to 0, but we should look for a solution which remains bounded as r tends to 0. And the boundary condition that on the circumference of the circle, that u is u0 for all t positive, becomes u of a t equal to u0. Okay, so what I have said, I have just written there. Okay, so we require the solution to remain bounded as r tends to 0 and also for all t 0 to infinity. Okay, so we'll make again one more reduction. So put v of rt equal to u of rt minus u0. So u0 is the boundary condition. So that's the boundary of the cylinder is maintained at that temperature. So just subtract that. And again by linearity, so the equation for v is same as the equation for u, but only there is some changes in the boundary condition. Initial condition becomes u1 minus u0 and boundary condition become 0 because we are subtracting u0. Okay, so this is the problem. We are going to obtain solution in an explicit form. Okay, so we are going to use method of separation of variables, and in the process we do require some knowledge of, in this case, knowledge of Bessel function of order 0. So this is usually denoted by J0. So this is one occasion where we do need this knowledge of Bessel functions and their properties. And at some other places in this course also we do need the knowledge of this Bessel function and its properties. So you can refer to any good book on special functions including these Bessel functions, and for your reference we are going to prepare some notes on the various properties of the Bessel function we are going to use in this course, in particular this example, but we are not providing any proofs. By no means the properties are property we are going to use are easy ones, they need proof. So you should learn from some good book on Bessel functions. Okay, so this, if we look for solutions in the separation of variables form, so we write v r t equal to r of r and t of t. So r is a capital R is a function of small r only and capital T is a function of small t only. Okay, and when you substitute this form in the given equation, namely dv by dt equal to d square v by dr square plus 1 by r dv by dr, this is the usual process. So we get this equation 1 by t equal to dt by dt equal to 1 by r d square by dr square plus 1 by r dr by dr, and right hand side is only a function of small r and left hand side is a function of small t only. So this must be a constant. Okay, so if you just use the equation for capital T, the solution is general solution, that's a first order ODE. So T of T will be equal to A e to the lambda t, where A is a constant. Okay, so these are important requirements. So we want this V to remain bounded as r tends to 0 and all t up to infinity, and that forces this constant lambda to be only less than or equal to 0. So if lambda is positive, then as t goes to infinity, this capital T becomes unbounded, and so that's not a required solution. Okay, so we want bounded solutions. Okay, again when lambda equal to 0, you consider the other equation. Okay, so then we get d square by dr square plus 1 by r dr by dr, and if you look for non-constant solution of this equation when lambda is 0, so that is 0, the non-constant solution becomes unbounded as r tends to 0. Okay, again we don't want that. We want the solution to remain bounded as r tends to 0, and that forces lambda to take only negative values. Okay, so we put lambda equal to minus mu square, and we may assume that mu is positive. Okay, and then so this solution for capital T, we get T of t is equal to e to the minus mu square t. And what about the equation for r? Now we put lambda equal to minus mu square, and then the equation for capital R is d square by dr square plus 1 by r dr by dr plus mu square r equal to 0. Okay. And so from here we start the journey to Bessel's function. So this equation can be transformed with a simple transformation to the standard form of Bessel equation. So what this equation we will write in the notes, and for the time being just you if you have studied it, well and good. So the solution of this equation, the general solution of this equation is given by r of r equal to, so I can always put a constant multiple, but that we already put in t itself. Okay, so we can just write r of r equal to j0 mu of r. Okay, so where j0 is Bessel function of first kind of order 0. Okay, so then the solution is given by this multiplication of t of t and r of r. Okay, and now we have to satisfy this initial condition and boundary condition. So let's take the first boundary condition. So see, this is given only at r equal to a, so that big R function we have to worry about that. So in order to satisfy the boundary condition at r equal to a, we must have this j0 mu of a equal to 0. Okay, so it's an important property of this function, Bessel function 0. So j0 has an infinite number of positive zeros. Positive roots are zeros. Okay. So that's an important property of this j0. So this also has close connection with trigonometric functions, our sine and cosine. Okay, so you just put them in some order. Okay, so let 0 less than alpha 1 alpha 2 be the positive roots of j0. So you list them. Okay, and another important property is that they are all simple roots. Okay, so this, so j0 alpha k is 0, j0 prime alpha k is not 0. Okay, they are all simple roots. Okay, so thus this mu we started with, this constant mu has to take the form that alpha k by a. So mu a is equal to one of the alpha k's. So that mu has to be alpha k by a for some k to 1 to a. Okay. So if you just pick one k, so the solution is given by p r t equal to some constant into e to the minus alpha square by a square t into j0 alpha k by r. Okay. So by linearity of the problem, equation and boundary conditions, so we can write a general solution uh, of the given problem as we are t is equal to ak's are some arbitrary real constants into exponential alpha k square by a square t j0 alpha k a by r. Okay, and now so we have another condition to satisfy, namely the initial condition. So initial condition is v of r0 equal to u1 minus u0. Okay. So uh, just substitute t equal to 0. Okay. So again there is no problem of convergence for t positive because of the properties of this Bessel function j0. Okay. There is absolutely no problem. So in order to determine this constants ak to satisfy the initial condition, so formally you just put t equal to 0 here, so we get u1 minus u0 equal to this summation k equal to 1 to infinity ak j0 alpha k by a r. Okay, and in order to determine this ak, okay, just like we do in Fourier series, we do require some orthogonality properties of this G0. Okay, so I'll just write them here. Okay, just let me use some different pen here. Okay, so these are the properties here. If alpha, beta are distinct positive roots of J0, then so we have this orthogonality condition integral 0 to 1 x j0 alpha x j0 beta x dx equal to 0. Okay. So we say that, so if you consider this family, so we consider this functions j0 alpha x alpha positive root of So this collection of functions over the interval 0, 1, they are orthogonal with this weight. Okay, so they should just remember there is a weight here. Okay, it's not just for trigonometric functions, there is no weight there, weight is 1, but for this Bessel functions there is a weight there. Okay, so this is one important property. And what happens if I take alpha equal to beta? Okay, so let me just take that one. So let me just, so 0 to 1 x j0 alpha x j0 beta x dx is 0, and this x, so I am taking alpha equal to beta dx, and that is half j0 prime alpha. So as I commented, all the roots of the function j0 are all simple, so this is strictly positive. Okay, so in fact this can be expressed as j of 1 alpha square. Okay, so this j1 is Bessel function of order 1. Order 1. Okay, so we have the relation j0 prime of x minus j1 of x. So all these properties can even be deduced from the Sturm-Liouville theory we study in ordinary differential equations, Sturm comparison theorems, and so many other things. So there is another one in this computation we require. So this is just 0 to 1 x j0 alpha x dx. So this is, here we require this alpha to be a root of j0, but in this computation we do not require that. So this is just j1 of alpha, so alpha positive. Okay, so if you use these three properties, okay, then you so multiply this by x. So see, for example, here this r by a by our choice, so if we call it x, then x belongs to 0, 1. Okay, so it fits into this orthogonality conditions and normalizing conditions, etc. So you multiply this both sides by r by a, so r by a you call it x, and then again multiply by j0 alpha kx, and then integrate from 0 to 1, use this orthogonality conditions, and then other two conditions here. Okay, so only one term survives every time, so whatever j0 alpha k term we multiply here, only that term survives and there is a AK there, but then there will be some integral and those integrals are evaluated by these two formulas, and when you do that computation you get this AK is equal to twice u1 minus u0 divided by alpha k j1 alpha k. Okay, so this both the terms in alpha k is positive by choice, and this j1 alpha k is nothing but j0 prime alpha k with negative sign, and since alpha k are all simple roots, so this is also non-zero. So this AK is given by this number, and at this uh, stage you also realize that this u1 minus u0, this can be replaced by any function phi of r by a, okay, and that you express as a summation using this Bessel functions, and that is termed as Fourier-Bessel expansion. Once you prove this uh, family of functions is an orthonormal family with suitable normalizing constants, so orthogonality conditions are there, and then you divide by some normalizing conditions, so it becomes an orthonormal family. So then there is a general theory. Okay, so you can expand uh, any suitable function uh, in terms of this orthonormal family, and that is in this case, since it involves Bessel functions, so it is termed as Fourier-Bessel expansion. Okay. So finally, okay, we have the formula for all the AKs. Okay, and then the solution U. So remember, from U went to V. So now it is U equal to V plus U naught. So we have got only V here. So we have to add U. So and that is given by this. So in explicit form. Okay. So to arrive at this explicit form, so we have made use of several things here, uh, assuming that their validity, so that will provide in some notes, but so you have to really look into some literature in order to prove these relations. They are important relations, and we also need this knowledge of Bessel functions in some other situations during this course. Okay. So we'll also uh, give some similar problems in the assignments so that you can work out. So in only few situations we are able to find a solution in explicit form, and there is, so here we, assuming that the initial and boundary conditions do not vary in the z variable, we deduce this thing. So there is also possible to make this everything depending on z. Okay, so still one can work out with separation of variables, but computations are more lengthy and more involved, and the expressions are also look more complicated, but that's also possible. So you can include z variable in this analysis. Okay, so with that uh, remark, so we more or less finished this topic of heat equation. So again, one more remark. So we have included uh, so many topics in this PD course. So it is not possible to uh, give all the details about any one particular topic. So here our aim is to provide a general viewpoint, and hope some of you may get interested into studying further topics in partial differential equations in any of them. Okay, each topic here we have chosen is a material for one semester or even more. Okay, so you can imagine, so we cannot provide all the details of your heat equation or wave equation or even Poisson equation. So this is just a general viewpoint we are providing, hoping that some of you will take up further study in these topics. Thank you.